Hello guys, Nikolaj here. So in this video I want to present to you a project I've been working on, namely a Turing complete smart contract. So in the bulk of this video I will explain just exactly what that means really. But in short, you have to contrast that Neo is a blockchain that has a Turing complete virtual machine, meaning that as opposed to, for example, the computations you can do on Bitcoin, on Neo you can basically solve any conceivable numerical problem by implementing some programs and functions in the smart contracts, and it will do just that. The smart contract I will discuss today is one that is itself Turing complete, meaning that you can program and even store these programs in the context of the smart contract. To be more precise, it's really an interpreter of classical Turing machines, and I will show you some examples in a minute. And applications are that you can, using this, for example, program parts of your smart contracts, modules or functions of your smart contracts long after you have deployed them, right? So you can, either you take this concept and instead of having some fixed function modules, you let the contract access the library with various functions that you can implement and configure the smart contract while it's up in the blockchain, or you can access the Turing complete smart contract, which comes with a programming library and access any functions, in particular finite state machines. You could use the finite state machines for verifications by checking properties of sort of passwords, for example. Or if you think further, you have a decentralized library of subroutines that you can work on together and access from everywhere without using your own computational power, because you can have the nodes executed for you. Yeah, okay. So to break it down, I will now show you invocations of the smart contract using the graphical user interface from Neo, and you can also do it with Python now. Then I will shortly try to we'll see how short it will be, but I give you a historical context for how Turing machines were conceived and what it really means and how it is possible and why it is interesting. And if you know all that, then after having watched the invocation of the smart contract in the next minute, just skip the whole computer science introduction, and in the end of this video I will go through the C# code in which the Turing machine interpreter is written and discuss the smart contract. And if you have not seen Neo smart contracts before, then that will also be an introduction to the whole structure of Neo smart contracts. Okay, so my battery just died out. What I was going to say is that before we go into this small clip of how you can use the Turing machine interpreter, I want to add that in this clip I showcase how you could use the Turing machines that you run also to access information from the blockchain. For example, I query the timestamp of the current block, but in the code that I also show you at the end of the video, I just do the raw Turing machines. In a next step, one may include opcodes or trigger codes for the Turing machine to access all the system functionality, and then you can basically do your own infrastructure of smart contract actions within the Turing complete smart contract. But in practice you would actually not want to use C# or any high-level language to write that, but to be more efficient, literally go and assemble the smart contract code for that. And in future videos I will actually go more into the virtual machine for Neo, because I want to implement some more or much more modern languages. Turing machines are 80 years old, and I want to come from the complete other end and will actually do some dependently typed languages, verifiable smart contracts, and still have a very general functionality to make full use of what Neo has to offer. Okay, so let's get into it. Okay, so this is the graphical user interface where I use the address of my contract to talk with the blockchain and invoke it. And it takes several parameters. First is a string where we say how we want to call the program which we will upload. And the second argument is also a string, and that's the code of the program, which in this case is just this ugly sequence of digits and some symbols. And then I can deploy it, and I get notification back from the blockchain, and it says here, program code successfully deployed. The NEP5 standard token, that's not me, by the way. Okay, so since it's deployed, I open it again, and now I want to call the program that I just uploaded. And this time, the second parameter is not the code of the program, but instead the input for the program. And this was a code for multiplication, and I will multiply 2 times 3, and that's encoded in the way you see there with ones. And also beyond that, there are some other parameters that will get clearer at the end of the video. So this is the size of the alphabet and the state of the machine, and then the maximum runtime which I will allow the machine to run, and so on and so on. And in the end, I invoke it, and it multiplies 2 and 3 together, and 6 is the result. Of course, I can do this with some other numbers. I kind of cut through this video because I wanted to make it short, but 3 times 3 is 9. So you can really deploy any algorithm that a Turing machine can compute. Then I play the same game again. I upload another program, and that's a program which tells you yes or no whether a string is of length power of 2. So whether it's 1, 2, 4, 8, 16, these will be allowed strings. And that's the code that does that. I explain later why that's the code. And yeah, I deploy it, and it would tell me successfully deployed. He streams a lot of data several times, but in the end, like the last one is that it's successfully deployed, and then I do the same game and give it some input. And in this case,
I give it a string of 4 ones, which is a power of 2. And so it says accepted, yay. It calculated that 1111 is a string with ones, so many ones as is a power of 2. And for demonstration purposes, I do the same thing again, but this time as an argument to this power of 2 algorithm, I give it a string that's 5 ones long, and so that's not a power of 2, and it rejects the string. Okay, and I play the same game again, I deploy addition, and you see here, and I have some commas between the codes for the string, and that's also accepted. And I cut the video down, but here in the end you see I also let the Turing machine talk with the blockchain. It saves the timestamp, and you have some exception codes, and detect one that what you see here in the middle, that's a program which just detects if a number has, if a string has a 1 in it, and that would be a classical example of a finite state machine application for which this smart contract is also suited the best, because a finite state machine is very simple to program, as you will see later.
Okay, so to explain Turing machines, and in particular universal Turing machines and universal computation, Turing completeness, I want to give a little bit of an historical context. I suppose formalized logic reasoning can be said to start with Aristotle over 2000 years ago, but a major turning point in the history was Gottlob Frege's Begriffsschrift, which was a work around 1880, where he introduced formal logic, a predicate logic, which is very similar to what is the de facto standard used today in formal mathematics and math departments. Around that time, Georg Cantor, another mathematician, came up with his famous set theory, and that's a theory of mathematics which can also be written down in this logical language. And it was discovered that you can essentially embed any mathematical structure in this set theory. So in this sense, it works as a framework to do any kind of mathematics, and you can thereby formalize mathematics. I mean, of course, people in math are generally, we're always quite rigorous, or more rigorous than in many other fields, but the developments after Frege took this notion of rigor or formalization, at least, to a new level. And even more so, it was then a shock when there was an inconsistency found by the philosopher and mathematician Russell in set theory, and then came this phase which is known as fundamental crisis, or crisis of foundations of mathematics. And people like David Hilbert became even more obsessed with proving consistencies and putting everything on a completely rigorous standalone basis. And out of this challenge grew many problems that were essential for the 100 years that came after Hilbert. For example, in the beginning of the 30s, Kurt Gödel provided his famous incompleteness theorems, which directly sort of resolve consistency questions. And closely related to that is the so-called Entscheidungsproblem, also by David Hilbert, in which he essentially asks for an algorithm that takes a language in a predicate logic, very close to what Frege proposed, and asks, hey, is any theorem I would take as an input to my algorithm provable from the axioms that we agreed upon in a given mathematical theory. So see, he basically asks, okay, say that's my mathematical theory, say that's my theorem, is this provable or not? Can I deduce this in a computational sense, plug and play and work through it and find out without any creativity, is this a provable statement or not? Is this possible? And this question was the driving factor that drove Alan Turing to his invention of the Turing machine, and that's basically the reason why we have this today. I mean, I guess if there was not Hilbert and his questions on formal logic, eventually out of practical need we would have ended up with computers, but it probably would have taken many more decades. Yeah, so you have the Turing machine, which is Turing's answer to the question. I mean, it's a little bit difficult to put yourself in the position of people 100 years ago, because today we have computers and every child has some idea what a computer program can do or what it cannot do. Basically, it can do many things. But back in that time, there were no machines which you can program, right? There was no programming. But the Turing machine, 1936, and the lambda calculus by Church, 1935, so 1 year earlier, those are the first general programmable concepts or frameworks for processes. And what that means, general, or let's say how these far-reaching frameworks are more encompassing than previous systems, so why this was a big deal. That's kind of what I'm trying to elaborate in the upcoming minutes. Okay, so I've written down some simple questions here, really. They are questions that are related to the examples that I showed in the GUI for the smart contract, the examples. And there are also questions that will concern us in the rest of the videos. But really, these are just, example questions. And the point is that a universal Turing machine can solve, in particular, any numerical problem that you can, encode in a function, in a question of, this is the input, this is the output. If there's, and really that's the Church-Turing theorem, if there is any way of computing the result of such a function or a problem, then a Turing machine, that's the hypothesis, can already solve it. And this is more, it's not really a question of mathematics or physics or computer science. So that's more a hypothesis of the world. And okay, so but back to these simple questions. So I'm not sure if you can read it, but that says, what do I get from adding 2 or 5 or 9 and 13, or 200,078,000 plus 3096. The point being, there is also an incarnation as a Turing machine that solves exactly that problem, and that's the Turing machine that I uploaded before. So that's at least one of them. There are many probably, but so one Turing machine is like one algorithm. It stands for one algorithm that solves a particular problem. And in the same sense, here we have, the question: is this string 1111 of length a power of 2? So, in that case, we know that I recognize that as 4. Humans are very good in recognizing items if they're not more than 7. If you see 6 monkeys, you only have to look quickly and that I saw 6. If they are like 10, then it gets harder, and if they are 100, you cannot tell the difference between 100 and 110. But here, you can solve it in your brain. But if I give you, a huge string, which is 2 to the power of 30 plus 1, you have no way of solving it, like of seeing it that it's power of 2, and so you have to rely on some counting, right? And again, there is a way of constructing a Turing machine, as I have basically shown you before, that does exactly that. You can construct a Turing machine that takes as input any string and tells you, hey, is this power of 2 or not? And in a similar fashion, I have here a string. This is 0, 0, 0, 0, 0, and the question is there a 1 in the string? Or you can ask, if I write down the sentence, that was tongue-in-cheek, and I don't know how to write tongue, because I always forget. Is there an H in tongue, right? You look at it and say, oh yeah, I see an H there. But if you want to recognize some patterns in a more complicated structure, then you might want to have an algorithm. And I can write a Turing machine that discovers if the sentence tongue-in-cheek, the expression, has an H in it or not. And very similarly, I uploaded a Turing machine that solves the problem: is there a 1 in this sort of string or any string? And what's interesting to note is that these are 2 problems, but they are actually quite different. There are many incarnations of computing procedures. There are many sort of algorithms, and one which we will discuss in the next minutes is a finite state machine, so-called finite state machine, and that's a procedure that can also compute stuff. For example, a finite state machine can find out if some string has some character or some subword, but a finite state machine, for example, would be an example of a machine that you cannot program, or you cannot arrange its moving parts, let's say, so that it solves this kind of problem. So here we see that there are some, that it goes in a very computer science theory direction. There are some problems that are harder than others in a very technical sense also. And these sort of problems, there's complexity theory, but these 2 problems, they are literally in another hierarchy, so to speak, in different levels of a hierarchy. And this way up there is called the so-called Chomsky hierarchy. And you can view these kind of machines as ways of recognizing features, right? And it's also related to how complicated the inputs are. And there is the hypothesis, which is tied to the Church-Turing hypothesis, that a Turing machine is already the strongest machine, right? So while there are there are frameworks for formulas and frameworks for computing that cannot solve some problems. If a problem can be solved at all, it can be solved with a Turing machine. Okay. Okay, so as a bridging step to Turing machines, we're going to discuss finite state machines, okay? Here are 4 problems, all incarnations of the same problem, namely, do these strings, right? Do these strings contain a 1 or not? And I mean, obviously, okay, yes, yes, no, yes, okay, that was easy. However, again, let's say you have, you know, a file of 10,000 symbols, and they are not just zeros and ones, but they are like 60 different symbols, and you cannot see at first glance do they have a 1 or not. You have to write some small program or at least some procedure. And so let's say you don't have a computer, but your little brother is very bored and you want to give him this task. But it's a very small child and you don't know, if he will be able to solve this task himself, come up with a strategy to go through all these things. So you describe to him in detail how do you solve this problem. And the description of a finite state machine as well as a Turing machine later is basically a fixed set of rules. You only have to learn these rules once. It's like chess, and you play the game, and by just going through these steps, these fixed steps, without being creative at all, you end up at the right answer. That's the idea. And the challenge to program is to find the right rules, basically. Again, these rules are also just variations of some core items in this framework, and in this case it's the finite state machine. So here's how it works. The algorithm that solves this kind of problem works as follows. You go through the string from left to right, and you have this sort of scheme. So there are 2 states, it's a finite state machine. This is the start state, that's where we start. That's like my token on a chessboard, it starts here. That's the acceptance state. So if I end up here in this state, it's basically a yes. And I go through the symbols in the string, and I follow the rules indicated here. So if I see a 0, I go along this arrow. If I see a 1, I go along this arrow, and the same here. And what happens is the following. So I start here, I see a 1. I see a 0, sorry. I see a 0. Stay at the same place. I move 1 to the right. I see a 0 again, here. 0 again, here. 0 again, here. Then I see a 1, I move there. And next, 0, 1, whatever happens now, I never move away from the A state, because the arrows end here and there's no arrow back. And so as soon as I see 1, 1, as soon as I see the symbol 1, I end up in this acceptance state, and I go through the end, and then I evaluate, here, where am I? Am I here where the A is, the acceptance state, or not? And it says, yes, A, there's an A. So indeed, in this string, I know there was a 1. Okay? And same here, so I start here, I see a 0, I see a 1, I'm there. Here, 0, 0, 0, 0, 0, 0, and then I evaluate and say, oh, my end state is not the A state, not the acceptance state, so there cannot have been an A in it. Because this finite state machine, this board game, is an incarnation of the algorithm that finds out whether or not there is a 1 here. And of course, this looks kind of simple, but I can reprogram this machine on the fly. For example, so let's say I accept strings that have either one or more than two ones, but I reject strings that don't have a one, or I reject also strings that have exactly two ones, right? So that would mean, does this look? So if it has, like, for the start, it will look exactly like this. So if there is exactly one, like this would have exactly one, so then I would end up in the six-happened state. If there are two ones, right? If I end up going through the whole string and there are exactly two ones, then I would not be allowed to accept it. So there is probably another state that I go away from the acceptance state. If there's a 1, if there's a 0, that's okay. And then if there is another 1, if I end up here in this state, this is not an acceptance state, but if there is another 1, then I would have 3 or more 1s, right? And I would accept it again. So I have to draw another acceptance state here. So that would be 1, 2, 3 1s. Here doesn't matter what happens. 0, 1. And what we see here is 0. So this is now an algorithm that solves the problem. Does this string have 1, 1 or more than 2 ones, but rejects strings that have 0 ones or exactly 2 ones, right? So that's a finite state machine with 4 states. And so I guess the idea is clear. And you know, in a machine, on a machine like that, it has a processor with a certain, that runs at a certain frequency, so on so many gigahertz or whatever, and you can implement finite state machines by, you know, the machine's frequency is like a heartbeat, and at every clap something happens, and this however you implement this puck moves, and this way you can solve a lot of problems. Basically, you can construct machines with a heartbeat that move your puck around, and have this kind of applications covered. For example, an elevator would be a finite state machine thingy, right? So you there are states like, well, the elevator is occupied, the elevator is free, and you know, if you press the button, then you reserve the elevator for you, then it will come to you. But if like in another level, if another person presses the button, that would be futile because you already called the elevator, because the elevator is either free or not free, and these kind of things. Or you know, if you have in London, they have these nice turnstiles where, you know, you put your card in, then you can turn the turnstile, but you cannot turn it twice. You cannot cheat. You cannot have your friend also go through. So the turnstile is either in a locked state, or if you put the card, then it's in a rotatable state and you can go through. But once you did the action of turning it, it's in a locked state again. Now these are kind of these finite state situations. Okay, and here finally we have an example of a Turing machine. We had this question before. Is this string, the input string, for example 1111, of length power of 2? So power of 2, that would be 1, 2, 4, 8, 16, 32, 64, 128 and so on. You know, you pass it some string, and there are some strings which should be accepted. For example, if the string is of length 8, and most strings would be rejected. So string of length 100 would be rejected because it's not the length is not a power of 2. And as I said before, the finite state machine can actually not solve the problem, and the reason is that you can basically not count with a finite state machine. For these kinds of problems, you can show that you need an internal storage that keeps track of where you are. The finite state machine can only see the state in which it is in, but it has no track record of how it got there. But a finite state machine is therefore not as computationally powerful as a Turing machine. And a Turing machine is stronger because it can actually solve this problem. And there are power levels in between. There are some machines or some concepts of algorithm or these kind of board games or frameworks that are in between in the Chomsky hierarchy. But the Turing machine is already the strongest, and I will show you how a Turing machine computes whether a string is power of 2 or not. Here we see this kind of board. We have 8 states, so that's bigger than the finite state machines we looked at before, but that's not the point. The error are the same with the numbers telling you where to go, and in that case I consider an alphabet with not just 0 and 1 but also with 2s, but that's a minor detail, that's not really relevant here. What's relevant and what is actually encoding the Turing machine completely are these numbers that I wrote on here, and these numbers are exactly the numbers that I uploaded in the GUI clip at the beginning. So what these numbers encode is this state diagram and more. So for example, if you are in the state 1, the state with indexed with 1 here, that's this one, and you see a 2 on the string, you go back there, and this information that in the state 1, given a 2, you go back to state 1, that's also encoded here. So this is the column given a 0, given a 1, or given a 2. And if you are given 2, then that means you look here at the 3rd row, and the state where you have to go is in the 3rd column, so that's that. Right, and you go back to 1. Or if you are in state 3 and get a 1, you go back to 2, right? So that's state 3, given a 1, you go back to 2. Or state 4, given a 0, you go back to 1. This is a 0. So the third column here is just information that's also captured in this state diagram, and that's the same thing like as with the finite state machines really. But the other numbers are different. So the difference between the Turing machine and the finite state machine is that while the finite state machine was only walking over the string, over the input string from the very left to the very right, step by step, and moving on the board. The Turing machine also moves on the board, but two things. It can also walk in other directions, if you want, even jump around on the string. And also it can write back on the string. So it has the possibility to load information back to the string, and Turing in his paper describes this as a sort of tape. You have an infinite tape. In the middle you put the input string, right? You have infinite tape, you put your input string, and then you walk over this tape. You walk over your information like with the finite state machine, but you walk left and right, and you also write back to it. And what this says is, so given you're in one of those states, let's say the state number 2, right? And you get, what's interesting, right? And okay, the simple thing that's very similar with the finite state machine is, let's say you are in the state 2, somewhere on the string. You're somewhere on the string, you're in a state 2, and you read from the string a 2. Then in the next step, you are back on 2, right? And the first number here says what you have to write on the tape. In this case, you just write back a 2. And the second index tells you the direction in which you're supposed to go. And in this encoding, a 1 means you have to go to the right, just with the finite state machine, a 1 step to the right. A 0 means you just stay where you are. And a 2 means, I chose the 2 to denote you go 1 step to the left. Right? Okay, I hope this was not too confusing, but we can try to check if this string is length order of 2, right? So give me some space here. Okay, so I write down the initial string. You imagine this being on a tape, on an infinite tape, and I start here in my starting state as 0, okay? So in the state number 0, I read a 1, so I'm here, right? This is the 1, that's the first. So what happens now is, I will write down a 0, I change this to a 0. I go to the right, and I move to the state 1, so I move over there. Okay, then I see another 1 here, right? So that means I write down a 2, state 1, no, right? I write down 2, and I move to the right, and I go to the state number 2. In the state number 2, I see again a 1, I write down a 1, I move to the right, and I go to the state number 3. In the state number 3, I see a 1, I write down a 2, I go to the right, and go to state number 2. Okay, so you see how I changed the tape, and this will not continue. Since I changed the tape and come back and forth, the whole procedure can take longer. But I can spoiler alert, since this is power of 2, I will eventually end up in the A state. So here is basically a blank, and in my convention that means I didn't say that before, but that's the 0 is basically the blank symbol. So imagine here as more zeros, left and right. So here I'm in the state 2, if I'm not confused, right? I see a 0, I write a 0, I move to the left, because that's a 2, and I'm in the state 4, 0, 4. So, okay, I hope this doesn't take too long. So state 4, I see a 2, I write a 2, I move to the left, and I'm still in state 4.
Okay, so what we have here is a website in which someone implemented 5 Turing machines, and they correspond to the arithmetic operations. Here I do what I did before, and multiply 2 and 6, and you can run it and actually see the Turing machine perform, which is pretty neat, I think. Right. And I will now then go through this a little bit more slowly. Let me reset. And so we see, well, I step through this a little bit so to get to some interesting point. Okay, so here we are under state 4, and next will be 5, and depending on what we have here, it's a blank symbol, and the next is a dot, so we will have the state 5 for the dot. And here we write a dot, but there's already a dot, and we move to the next 5, and there will be a blank symbol, so it will jump over, right? And so the next is step 6 with a dot, and now 6 with a dot again, and so on and so forth. So it's completely deterministic. And yeah, they also have the factorial function, which takes like forever. Like if you do 5 factorial, that will run, and on the smart contract costs a lot of gas just for this simple arithmetic operation, right? Right, here, this is exactly the code that I deployed, so that's a very short one. For multiplication as well as for addition, although I think I didn't show that, but so this is just, 4 states.
Right, at 2, I move to the right, I am in state 2, I see a 2, I move to the right, I write a 2, still here, and I see, okay, I mean, I don't want to make the video too long, but you see, it moves left and right, chuck, 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 chuck. It works exactly according to this board and these instructions. And eventually it will like override this tape a couple of times until there are exactly the symbols that lead it to the acceptance state. If this is a power of 2. Of course, the programming of this kind of machine is rather complicated because you have to think over some edges. If you know some theorems, then you can reduce this the programming challenge a little bit. But this kind of Turing machine is also suited for, of course, just to finite state machines because they are very easy to program. In that case, you always, in the finite state machine, right? You always write what's already there, and you just always move to the right, right? But you have seen in the GUI that I use exactly these numbers and it works. And for demonstration purposes, I now show you this kind of stepping through this game with addition. And gladly for you, I will not do it on the whiteboard, but I show you a website that has these arithmetic Turing machines implemented. Okay, and I want to now bring this one point home, that what we did here is construct some algorithms, basically, to solve particular kinds of problems. And what Alan Turing finds in 1936 in his famous paper is that, okay, he comes up with this kind of Turing machine, with this approach, with this encodings for algorithms, and then he discovers he can actually, as input, not only take the input for the problem, but what he can do is find the Turing machine, right? Find a very complicated machine that follows these kind of rules, and has this machine be fed as input the encoding of another Turing machine with together with some input, with the effect of the the big Turing machine simulating the actions of the other Turing machine that's encoded on the tape. So you have this big Turing machine called universal Turing machine that takes two inputs basically, all on one tape. On the one hand, just the normal input. On the other hand, the encoding of the algorithm that describes a Turing machine for a particular problem. And if you run the universal Turing machine, then the states will move exactly in a way that the big machine simulates the actions of the small machine and thereby solves the problem at hand. That is to say, the universal Turing machine can be programmed to solve any problem. Because whenever you can draw a whiteboard Turing machine to solve a particular problem, maybe addition or maybe recognition of this kind of grammar, so you know, the length of string or whatever feature the string has, whatever kind of Turing machine you could write down on a whiteboard, you could also encode it and feed it as input to this universal Turing machine, and the universal Turing machine that will then solve your problem because it has the programming in form of another Turing machine. And I mean, maybe I'm not sure how good I describe this, but the point is this, that this is what programming is really. You have your computer, and your computer, you know, I have a computer here, incidentally. You know, this is some PC, and it works as a universal machine in the sense that on the hard drive I can save files, scripts, they may be Python scripts, and I can have the big computer execute the scripts, and the scripts are, so to speak, Turing machines that solve a particular kind of problem, and writing the computer program on my computer amounts to finding out, oh, how do I solve this particular problem, and the computer is the universal machine that takes the script, the Python script, as an input and does the whole job for me, right? And so that's the inside of Church. In the lambda calculus, you do a similar thing, I guess. But here we are about Turing machines, and this is the achievement basically, to see, hey, not only can I do one purpose algorithms, but I can also put them in the framework of this universal computation. And the computer here is a universal machine, can solve any problem. And in that sense, yeah, it's a universal machine. And whenever you have a programming language which you can use to encode any, problem-solving algorithm, you say the language is Turing complete. And for example, the Neo virtual machine, the virtual machine on the Neo blockchain, is, as opposed to Bitcoin, for example, it's Turing complete in the sense that you can take any problem and write down an algorithm to solve it and package it in a smart contract, and that makes the virtual machine Turing complete, right? You can find some smart contract that solves your problem. And going back to my smart contract, my smart contract is Turing complete in that you can also take any problem and upload the solution to the problem in form of the algorithm, actually in form of a classical Turing machine, and have the smart contract execute this smaller Turing machine and solve your problems. Okay.
Okay, so welcome to the last part of the video where I will go through the code, the universal Turing machine, if you want. So that's, about 150 lines of code. To give you an overview, the Neo smart contracts are always called by calling the main functions, and then you can pass whatever arguments. That's what you saw in the graphical user interface. And here I hold the main function very short, and it delegates calls to two other methods, either deploy or execute the Turing machine. Deploy will be a very short code, and the run command has, after some initiations and reading in of the config parameters, the main loop where the code steps through the Turing machine that is loaded, and has all these head variables. That's the head that writes on a tape, and then it figures out where to take the information from, so that you write the right character back to the tape, change the state, and then if the state is an accepted state, end up. Okay, so I just quickly browsed through that. I will go step by step through this code in a second. I choose to return integer values, so that when you want to call the smart contract from another contract, that you can evaluate, hey, what happens, accepted, rejected, or exceptions or error messages. And I will get to this commented out section later. And then there are some utility functions, right? So for user convenience, I work with strings. You upload Turing machines, for example, in strings, and you provide the input as string instead of another big array of integer values. But this assembly function, that's a function which is called above, does exactly that. So you take the string and you translate it into an integer array, and to get, 35 different possible numbers into it, which specifies basically the alphabet that you can use. I make these conversions from string to integer here, and I assign particular numbers to particular characters. And then there are some functions that I use above, right? So since I didn't want to use negative numbers in case this is ported to a code where you work with bytes and bytes cannot be represented, I'm on the safer side if I use these negative steps in a form that I can still pass positive numbers. So, as I said before, number 2 represents a step to the left, and this is kind of this correction that is encoded in the function and used further above. And also for user convenience, and I will not, print out the whole tape at the end of the function call to the notification row in the interface, either the graphical user interface or Python or whatever you're using. So what I do here is I just collect the number of ones, and this is the way in which, for example, I evaluate 2 plus 3 is 5, and the 5 is represented as 5 and not just a sequence of 5 ones here. And I didn't want to make it too complicated, but I wrote a bunch of conversion functions. Most of them are not in the code anymore, but these are, for example, ways to compress and uncompress output. So if you have a sequence of, if the tape says 771111 77, then it would print it as 343. So just a number of different characters. This way you could take long strings. If they are very repetitive, you could compress them into some other output that has the same information. But for simplicity's sake, I ended up not actually using them for the demonstrations in the graphical user interface usage at the beginning. Okay, so let's be a little bit more detailed. So what happens when you call the main functions, as I did, with some new machine key, right? The machine key or the program name would be something like mult or add or is power of 2 that I used in the beginning of the video. And then I pass the encoding of the Turing machine in the way I just previously described. You have this long sequence of numbers that is blocks that are states and rows that represents the state that you get, and then the columns say what you have to do. And if you read this from the left to right, you get one long string, and that's what I input here as a function. That's how I, for example, uploaded the multiplication code. And then there are some config parameters, and this will be clearer when we go further down to the code. The first thing happens is that the code logs the name of the program that you just called or that you just wanted to deploy. And then it looks for this name into the storage context of the smart contract. So in Neo, every smart contract can have an storage associated with it. That's a storage saved on the blockchain. And that's the command, how you retrieve this information, and you retrieve it as byte array. And so since this is since I put in at a later point the program codes as a string, but I read it out as a byte array, I call this bytecode. And in case there is no Turing machine stored with this name, then he will assume you want to deploy a Turing machine. And so that's why we have here, if this is empty, if there was no Turing machine found under this name, then you deploy under this name the code that you just provided. Otherwise, if there is already a Turing machine stored, like the second time, let's say, that you do the multiplication operation, when there's already code being uploaded on the blockchain, then it will take the bytecode as a machine, and as we have seen before in the beginning, interpret the code as the code that's supposed to be written on the tape, and together with the config data, run the Turing machine. Okay, so how does the deploy code look? That's very simple. So I just call the put function. Right here we use the get function to get the storage. Here we put the code under this key onto the blockchain. Internally, the Neo virtual machine has strings also just saved as byte arrays, and so that's why we can pass a string here and read out a byte array. And I log, well, successfully deployed, and I return with 0. So if you were to use the Turing machine to even deploy another, if you were used to use this decentralized universal Turing machine to deploy a Turing machine from another contract, then you would, for example, wait for this return value being 0 to know, oh, I have successfully deployed my machine. And now we look at the run code. So what happens here is that I pass the machine code as byte array, and I pass the string as the code as string, the tape code as string. But I really want to work with a byte array or with an integer array. And so I have to do some conversion. And for this, I have written this function assemble, which, as you can see, takes a string and gives you back this byte array. Let's take a short look at the assemble function at the bottom. So, okay, here it takes a string, I call this hex code. I initialize some variables. Then I create an integer array that's as long as this string, right? And then I go through the string and in the for loop, read them out as characters and convert them to an integer implicitly. Since here I take this character and I do this subtraction operation, he will internally compute the integer that's associated with that character minus the integer that's associated with the 0 character. And what happens here is that exactly, for example, if the character is 3, if you subtract the 0, then since internally the characters are also linearly ordered, numerically ordered, you exactly get the number 3 if you do this subtraction. And so this if clause filters whether or not the character is actually a character that represents a digit. So if I pass a 3 here, then this is bigger than 0 but smaller than 9. And then I add it to this assembly integer array. And what I do is I decide that I represent the number 10 as a capital A and go on. Number 11 should be a capital B. And this is exactly the code for that. So here we had the first 10 digits, 0 till 9, and so we continue with here. So if the character is an A, then this will be a 0 and a 10 will be added. If the character is a B, then this will be 1 and 11 is added. And then I return the integer array. And that way, for example, for the multiplication Turing machine, that actually required 16 states, and the 17th state is the acceptance state. And to encode that, I had to go over the number 9. And that's the reason why the string, if you remember, that I had to upload for the multiplication Turing machine had some capital letters in them. It's okay, that's assemble. Yeah, what I do here, the bytecode that I got out of the storage, I translate it back to a string, and this will be just some numbers. And I assemble both. In that case, that's interpreted as the Turing machine. That's interpreted as the sequence that's to be written on the tape. And yeah, well, then I have the data. Right. So one note is that if I pass some characters in the code that are neither a digit or a capital letter, then none of these if clauses will say true, and then this letter will be ignored. But since I initiated the byte array as the length of the string, this means I will have trailing zeros at the end. But that really doesn't matter. It's just more blank characters, so to speak. And for the Turing machine, they will not be used. And for the tape, this is just the way you would initialize the infinite tape anyway. Right. So here I introduce a handle, so that I don't have to use this long word. I need a row integer variable because the tricky part in using this very tight encoding of Turing machines is that at every step of the computation that I want to do, I have to access exactly the right character, for example, to know which character to write back to the tape. And later comes some little math that exactly does this selection of the right row and column position. And so I need this an integer row variable. Okay, and now we come to the config. So I define some default values for these 6 things. So the first one is the alphabet. Typically, for example, if you do computer science studies and work with Turing machines to prove some complexity theory stuff, you consider Turing machines with zeros and ones, for example. So that's a classical default. But if you want to have a little bit more effective computation, if you want to provide more complexity to the machines and the input, then you can also do that. And the implementation I have here is also pretty agnostic to that. You can choose whatever you want, and there will just be a lower and upper bound to how you scan through your machine and where the machine ends. Then acceptance state, you have to choose some value. I chose 1 here. Like on the diagram that I wrote before, I assign some integer starting with 0 to all states. Runtime, that will be it's not really time, it's rather the number of steps that you do. This is the number of steps for the loop. I can show you this later on. So the main for loop will be going through n up to the runtime. In the examples, I chose 200 for those. The default value would be the length of the tape squared, but that's arbitrary. Then I make a padding left and right for the tape, since the Turing machine can walk over the bound of the initial sequence to the trailing zeros, or to the blank symbols right there. So you want to do a padding to have the tape, the machine not run out of tape. I mean, of course, the Turing machine in Turing's paper is an imaginary Turing machine that has infinite storage space in the form of an infinite tape, and runtime is also not considered. In practice, in that sense, there is no Turing machine in the most strict of sense, but of course, those are only, let's say, small divergence from this concept. Okay, a variable of the head, that's basically the index over the tape that you are, and then the state index. And yeah, in case you provide an extra parameter, the first one will be alphabet, the second one will be acceptance state, and so on. The alphabet is something that is critical. If you do a Turing machine with 4 alphabet size and you don't change that, then it will be assume that's size 2 alphabet, and the indexing will be false, and you will run over the Turing machine in the wrong way. And if you get out of bound, then you will get an error. That's later implementation that we see. And if you choose another acceptance state, then you basically get another machine, then you just compute something different. It will stop sooner or later, right? Right, so I define tape length variable, and that's the length of the sequence I had before, plus 2 times the padding, so that's the padding before and after. Then I initialize a tape variable. That's basically the longer version of the sequence, right? And then I initialize the tape by, I go from the left side, take all the blank padding characters, and then I start taking the sequence that I provided as an input and write it on the tape. And then I have the tape initialized that I will use in the loop. Okay, and the main loop, this is just a realization of the steps in the example that I showed you just 20 minutes ago. So the important steps are the computation of the spot where we are in. These are just checks for errors and exceptions. That's where you write onto the tape. That's where you move the head, and that's where you move the state, right? And then already comes, are you in the acceptance state or not? Let's be a little more explicit here. So if the head wanders over the tape, then maybe you have just set a too small of a padding, right? Maybe you wandered over. So that is an exception. And you get returned the character free, and you know, oh, I can improve the config to get the result I want. And I do this because here I evaluate it, and I don't want the algorithm to break internally. You know, I don't want the C# to fail on the virtual machine, and I don't know what's going on. Okay, and here, I mean, you know, I don't want to spend too much time on that, but if you think about it, and this just works out, right? So let's say in the example that we had before, we had an alphabet of 3. We had this, 3 kinds of characters, the 0, the 1, and the 2, right? And the states made for these 6 blocks. And so here, if you do state times alphabet, then you jump in the rows, right? You jump per row. So for example, if you're in the second state, the second state had the index 1, the alphabet was 3, then you would have 3 here, right? And then depending on what you read from the tape, let's say you read a 1, then you would have to go 1 row further in this block of the second state, and that's why this gives the right row in principle. But then since there are 3 columns, you also have to multiply it by 3. And so, I mean, you can try. I mean, it works obviously, but you can think about this a little bit more. But that's exactly how you use the input from the tape and the knowledge of your state to get to the right position. Then, in case you're in the last row and go to the last symbol, and that's actually, and this number is bigger than the length of the machine, then you must have input some very strange data on the tape. You have jumped over the machine input, and so you provided an input that doesn't make sense for this Turing machine. So in this case, you get an error, and return value that tells you just that. Okay, and if you are through there, then your this row value is exactly the right spot of information that you want to write back to the tape, and so that's what happens here. The tape variable with the head position that you're just in is overwritten with the value that we read from the machine encoding, and then you move your head by doing plus minus of a small delta. That's either in this Turing machine either -1, 0, or +1, and this delta is really just a function that maps the number 2 to the number -1, so I get this right. I saw that before. And finally, the token on the diagram moves, so to speak. This would be the third column of this machine encoding, and this tells you what's the new state, and then you jump there. And in case you are in acceptance state, you stop with a 1. You write down here what's the state in which you're finished, and then you, as an extra information, as a side effect, you count the number of 1s that are on the tape. And if you implemented a numerical Turing machine that computes something and you represent the output as a sequence of consecutive ones on the tape, then this will be exactly the number that you were looking for, just like we saw in the graphical user interface, and you get your result. Otherwise, the machine runs and runs and runs, and once it goes over the runtime and is not in an accepted state, then in this case I implemented in a way that this says you are rejected. Of course, you could also, add another config and make explicit rejection state, but this is also since we already have finite runtime, this is also a way to go, because if you can implement this kind of rejection state where nothing happens anymore by just staying on the spot where we are. Okay, and finally I want to note that so here we do just a classical Turing machine, right? We have the possibility to recognize so-called unrestricted grammar, and we can do any numerical computations. But really, we can actually also write a new smart contract within the smart contract, because we could just do some opcodes. Here I call this query instructions in that case. We would just define some number. Here this integer would correspond to the symbol z in my assembly encoding. And then if the machine, you can include this line here above somewhere, and then if the machine would recognize, the character I'm reading is my query instructions, well then, since you're in the framework of the virtual machine, just call your system functions and blockchain operations. And in that case, that's what I showed in the graphical user interface example. I take the header and use the header to see, hey, what's your actually Unix timestamp, and I print this and notify myself this is the current timestamp. But I can also do storage here, right? I can here implement just some opcodes that say, well, take the current tape and put it to the storage with this extra key, or if you were to implement this whole universal Turing machine game with a more convenient language, something like Python or C#, and you upload whole Python scripts to the Turing machine and execute it, you could basically create a smart contract within this smart contracts. Okay, yeah, so I'm sorry this took another half an hour. I really, I was thinking like I'm through in 7 minutes. But I suppose at least if you did not see this kind of coding before, then you know quite a bit more about Neo smart contract programming and how this roughly looks. And I hope you subscribe and follow my upcoming Neo projects, which will also go more in the clean-cut new language directions, working with close to the virtual machine and exploring and explaining this fascinating world of Turing-complete smart contract programming and Turing-complete virtual machines. Thank you and take care.